Welcome to this ongoing series of lectures in group theory. Today we'll be looking at relatively prime integers. And again, the main tool for this lecture will be Euclid's theorem, which says that if we have two integers not both 0, where d is their GCD, then you can write d as an integer linear combination of the two integers. Alright, so here are the problems. And let's get started. So suppose we have two integers a and b, not both of them are 0. Then we say that the two integers are relatively prime if their GCD is 1. So as simple as that. Basically it's saying that there are no common divisors between a and b except for the trivial common divisor, which is 1 and -1, but okay. So that's what, and it's a very pertinent terminology. It's a good terminology. And here are some simple examples. If you see 8 and 15, they are relatively prime, clearly. And 8 and 12 are not relatively prime, since, for instance, 4 is a common factor, and 4 is... So therefore, the GCD is greater than 1. So that's one example. More interestingly, if we have a prime, and some integer, then p and n are relatively prime if and only if p does not divide n. So this notation means does not divide. So this is a very simple fact. Basically, suppose p and n were relatively prime, then p of course cannot divide n, because if p had divided n, then the GCD of p and n would be at least p. In fact, it would be exactly p. So that would contradict the fact that they are relatively prime. So one implication is clear, and the other implication, suppose p does not divide n, and now we want to prove that p and n are relatively prime. So suppose d is a common factor. Suppose d divides p and d divides n. So what could d be? If d divides p, and since p is a prime, d is either 1 or p, well, or -1 minus p, but that's irrelevant. We are just, let's say we are talking about positive divisors. So if d is equal to 1, that doesn't say anything. If d is equal to p, then you get that p divides n. But p does not divide n, so d better be 1. This forces that d is equal to 1. So that means that the only positive common divisor between p and n is 1, and hence p and n are relatively prime. So anyway, if anything is not clear, you can just pause the video and mull over this. Alright, so here is a very simple lemma that I have already given as an exercise before, but let me prove it here. So suppose we have two integers, again not both 0. Then those two integers are relatively prime if and only if what happens? There exist two integers such that the corresponding integer, the corresponding linear combination is 1. So let's prove this. So first assume that a and b are relatively prime. So assume a and b are relatively prime. Relatively prime is also written as co-prime. It's the same thing. So if a and b are relatively prime, then by definition their GCD is 1. So thus by Euclid, there exist integers x and y such that ax plus by is 1. So this implies what we needed. So in the other direction, assume ax plus by is 1. So if d is a common divisor, so let's say d is a positive common divisor, then d divides ax plus by, because if it divides a and b, then it divides ax plus by, which implies that d divides 1, which implies that d is equal to 1 because it is a positive number which divides 1. So This means that the only positive common divisor between A and B is 1, which implies that GCD of A and B is 1. So very simple. And this is a more interesting one, but I'm sure this also I have given as an exercise before, but I'll prove this properly. Let me get rid of the grid, although it doesn't really matter. Okay, so we have a prime and two integers, and suppose P divides their product. Maybe I should make a bracket. Suppose P divides the product of two integers. Then the conclusion is that P divides the first one, or logical, or it divides the second one, or it could divide both, of course. So this may be intuitively very, very obvious, but this is not so easy to prove. I mean, it's the proof that I'm going to write is going to be very easy to follow, but it's not a trivial fact. All right, so suppose P does not divide A. So then the goal is to show that P divides P. So this is what we want to prove. Now since P is a prime and P does not divide A, so this basically, this thing implies that GCD of P comma A is 1. This is what we just saw, that P and A are relatively prime, and therefore there exist integers x and y such that ax plus py is 1. Okay, so far so good. And here is a very interesting step. So we multiply both sides by b. Let me put that in a box. This is equal to b. Great. And now notice, P divides, of course, P, and by hypothesis, P divides AB. So P divides the left-hand side, which implies P divides the right-hand side, which implies P divides B. And that's it. That's the end of the proof. Very nice proof. I really like this proof. And yeah. A little bit more general, exactly the same proof is that instead of a prime, now you have a relatively prime integer. Suppose D and A are relatively prime integers, and D divides the product of A and B, where B is some integer. Again, let me make a bracket. Then it follows that D divides B. So it's just the previous thing. We have, instead of a prime, we just insist that two things are relatively prime. So again, this may be intuitively obvious, but you can practice this proof idea here so that you understand it. Okay, great. So this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I will see you next time.